Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on December 23rd, 2025, so about 1 day ago. This paper proposes a two-stage diffusion approach that first generates compact semantic video features for global planning, then refines them into V-latents, which the authors say converges faster and scales more efficiently to long videos. The paper is titled SemanticGen, Video Generation in Semantic Space. And as we'll see later, the idea of planning in a compact semantic space has some pretty interesting implications for both quality and compute. Figure 1 makes the main claim feel concrete because it shows that generating in a compact semantic space can still produce realistic, coherent videos. This figure shows a grid of text to video samples, including short clips and longer clips. The top rows highlight short generations like a bee over a flower and a neon city street. The lower rows emphasize longer sequences, where the scene stays consistent across many frames so the story does not drift. Figure 2 explains why the method can scale, because it separates high-level planning from low-level detail synthesis. The left side shows previous methods that go straight from text to VE latent tokens, then decode into video frames. The right side shows SemanticGen, where the text first becomes a semantic representation, meaning a compact description of what is in the scene and how it evolves, and only then becomes V-latents for final rendering. Figure 3 turns the big idea into a concrete training and inference recipe, so the model plans in semantics before it renders pixels. This figure shows 3 panels, and the key concept is the semantic representation, which acts like a compact scene blueprint. Panel A trains a semantic generator to match encoded video semantics after an MLP compression step. Panel B trains a V-latent generator to denoise V-latents while conditioning on those semantics. Panel C combines both steps from text to final V-latents. Table 1 shows that the semantic first approach mainly pays off on consistency and motion metrics for short videos, even if image beauty scores do not always top the chart. This table compares several methods across subject consistency, background consistency, temporal flickering, and motion smoothness, plus imaging and aesthetic quality. SemanticGen reaches about 99% on multiple consistency metrics, while WAN 2.1 leads on imaging quality. Base CT helps separate gains from extra training because it uses the same data and steps without semantic modeling. Table 2 shows that the semantic first pipeline stays more stable when videos get long, which is exactly where drift usually ruins coherence. This table summarizes long video scores across consistency, flickering, smoothness, and also a drift metric called delta M drift, meaning how much quality drops from early to late segments. SemanticGen posts the lowest drift at about 3.6%. SemanticGen also leads subject consistency and motion smoothness, while imaging and aesthetic scores stay in the same general range as strong baselines. Figure 9 shows that training a diffusion model in semantic space reaches usable video structure faster than training in V space. A semantic representation is a compact description of the scene, which is easier for the model to plan with than raw V latent tokens. The top block compares V space versus semantic space on a GIM interaction, and the semantic space row looks coherent while the V space row collapses into blotchy colors. The bottom block repeats that pattern on an aerial coastline scene. Alright, 2 takeaways stand out. The first takeaway is that generating a compact semantic plan before rendering V-latents can speed up training and improve coherence, especially for long videos where drift is the usual failure mode. The second takeaway is that putting expensive attention on fewer semantic tokens can make minute scale generation more practical. That is it for this episode of the AI Research Roundup. I am Alex, thanks for listening.